Hello and welcome back to the course on deep learning. We're finally at the part on autoencoders. So we've gone through quite a lot of different models in this course. We've already talked about artificial neural networks, convolutional neural networks, and recurrent neural networks, and that summarized the supervised deep learning side of things. And now we are in the unsupervised branch of deep learning, and we've already talked about self-organizing maps, Boltzmann machines, and now we're proceeding to autoencoders. So congratulations that you've gotten this far in the course, and it's been a very exciting journey, and now we're proceeding to the final stage. So let's get started. What is an autoencoder? Well, this is what an autoencoder looks like. And right away by the colors, you can tell the good news that we're back to the directed types of neural networks. And this is a directed type of neural network. The blue lines don't have arrows on the ends, but we'll just agree that it is a directed type of network and everything's moving from left to right. So how does a autoencoder work, and what's the whole purpose of an autoencoder? Well, just as the name suggests, an autoencoder encodes itself. That's the purpose of what it's doing, or the whole philosophy behind the autoencoder, that it takes some sort of inputs, puts them through a hidden layer, and then gets outputs, but it aims for the outputs to be identical to the inputs. That's what it's trying to do. That's how we're going to be training autoencoders, to set them up in such a way that on the output you get values which are equivalent to your inputs. And from that you can tell that autoencoders are not a pure type of unsupervised deep learning algorithm. They are actually a self-supervised deep learning algorithm, because they are comparing to something on the end. Remember, in Boltzmann machines, we didn't even have outputs. We didn't have to compare to any kind of labels or anything. And in self-organizing maps, the same thing. We didn't have anything to compare to. We were just looking for features. We were just looking for things. Whereas here, we are looking for things. We are looking for this hidden layer, which is also called the coding layer or the bottleneck. We're looking for how to structure it, but at the same time, we are comparing to the outputs to certain values, which are the inputs. So it's kind of on the verge between supervised and unsupervised, but we'll stick to unsupervised for autoencoders. And that's pretty much how it works. So you have inputs, they get encoded, and then they get decoded, and they're compared, and through that, the training happens. And as you'll see, because of all the things we already know from the previous parts of this course, it'll be very easy for you to understand autoencoders. They're quite a simple model when you combine all of the things that you already know. And right away now we just talked about the process, how they compare the outputs to inputs, and you can already imagine how information is propagated this way, and then you have gradient descent going the other way. So we'll talk about all those things, but just be prepared that this section is going to be, or this part of the course is going to be pretty easy for you, and you're going to most likely breeze through it, especially if you've been through the other parts of the course already. And one more thing on this slide is, what are autoencoders used for? Well, there's a couple of things that they can be used for. They can be used for feature detection. So once you've encoded your data, these nodes will represent certain features which are important in your data, and then you can just look at them and get those features out of them, or basically use those features in the future. They can also be used to build powerful recommender systems, as you'll see from the practical tutorials in this course. And they can be used for encoding. Basically, as they're designed, they are designed to encode data, and you could take data with lots and lots of values, encode it into a smaller representation, and then all you would have to carry around is this autoencoder or this decoder part and your encoded data. So it would take up less space. So that's another use case for autoencoders. All right, so that was a quick breakdown of the architecture of autoencoders, and now let's have a look at an example of how they actually work, so we can understand them better on an intuitive level. So there's a simplified autoencoder with just 4 input nodes and 2 nodes in the hidden layer. As we can see, we've got 4 movies over here and 4 movies over here. And what are these movies? Well, these are just movies that a person has watched, and we're going to be encoding the rating that people have left for those movies. So 1 means a person liked that movie, and 0 means a person didn't like that movie. And so that's how it basically works. And now let's have a look at how this information can be encoded through the autoencoder. And before we start, I just wanted to say that this example actually comes from this blog, probably Dance. It's a great blog. It's by a person who's actually a programmer who isn't a deep learning scientist, as I understand, but he really broke it down into good steps. So we'll link to this at the end as additional reading. Very great read here. But for now, let's just walk through this example. So here we go. Let's have a look at these connections. Well, first of all, without training the autoencoder, we're just going to come up with certain connections right away, certain weights, just to prove. So this whole example is to prove that it is possible. It is possible to take 4 values and encode them into actually 2 values and, carry that around and basically save space and extract those features. And it's just, this example is just to show that this whole situation is possible. So we're not going to worry about the training. We're not going to worry about anything else. We're just going to see, how is this possible? This sounds like magic, right? So let's see how this is possible. First of all, we're going to color our synapses in 2 different colors, blue and black, or light blue and black, where light blue is basically a multiplication by 1. So your weight is +1, and black is a multiplication by -1. So your weight is -1. And the other thing I wanted to mention here, in autoencoders, you normally use the hyperbolic tangent activation function here and here. And we're not going to be doing that. We're just going to, in this specific example, we're going to just worry about the weights, and we're just going to forget about the activation function for now completely. This will just help us understand everything on an intuitive level. So there we go. That's how we're going to structure this specific network, this specific autoencoder. We've already predefined the weights as such, and this will help us understand that everything is possible. This is just a specific example. So let's have a look at an input. Let's say as an input, we've got 1, 0, 0, 0. So the person just liked movie number 1 and they dislike the rest of the movies. So what will the hidden nodes look like in that case? Well, in that case, hidden nodes will be, this 1 will turn into 1 here, and this 1 will turn into 1 here, because blue is multiplying by 1. And these zeros, they will always just add 0. So basically, they're not going to contribute to the hidden nodes. And once you have that in, now let's calculate each one of the output nodes. So this is going to be a tedious process, but it's worth it. So there's our input going into into the hidden nodes, and now let's see what happens. For the top node, we multiply by +1 by +1, and we get 2. For this node, we get 1 times 1 equals 1, 1 times -1 equals -1. You add them up, you get 0. Here you get -1 plus 1 equals 0, and here you get -1 minus 1 equals -2. So those are your outputs, but those are actually preliminary outputs. In a autoencoder, we also have a softmax function on the end, and we have a tutorial on the softmax function in one of the very early parts of the course. It's a bonus tutorial, so now is the time to probably go revisit that tutorial if you skipped it at this stage. Basically, what the softmax function does in this case is it takes the highest value, so in this case R2, and it turns that into 1 and everything else into 0. So if you apply a softmax, you will get 1 where you see the highest value, and then zeros where you see everything else. And as you can see, this result is indeed identical to what we input into our network. All right, so that's the start. Let's have a look at some other cases. We're not going to be as detailed. We're just going to look at the results. So if you input 0, 1, 0, 0, you will see that you get a 2 over here. 0, 2, minus 2, 0. And when you apply the softmax, you get 0, 1, 0, 0. Again, identical. If you input a 1 over here, you get a 1 over here. If you input a 1 over here, you get a 1 over here. So as you can see, as long as in our data set we've got rows with just 3 zeros and 1 1, we can encode them into a small format where we just have 2 values. So we just have to have these hidden nodes. As you can see, every state is represented by a hidden node. So you have 1 1, you have 1 minus 1, you have 1 minus 1 1, and you have minus 1 minus 1. Every state is represented by a hidden layer, and then you just need these weights, the knowledge about these weights, to reconstruct your output. It's a very simplified example, and it was even quite, now looking back, it is even quite straightforward that if you have 4 states here, 4 possible states, then you have 2 by 2 combinations, you have 4 in total. But this gives a overview of how autoencoders work again in a very simplified way. They of course are much more complex than that. So here you can see much more sophisticated example where you have way more. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 inputs, 2 hidden nodes, and 11 outputs, and it still works totally fine. And this is a reference for additional reading to that same blog that we already mentioned. It's called Neural Networks Are Impressively Good at Compression by Malte Skarupke, and we'll include it in the additional resources, of course. So definitely check it out. Very nicely written, very easy introduction into AutoEncoders. In fact, I don't think it's even actually mentioned that it's AutoEncoders from the very start, just neural networks. And then in the comments, you can read that indeed they were talking about AutoEncoders. So have a look at that, and I look forward to seeing you next time. Until then, enjoy deep learning.